In this video, we'll talk about operations on radical expressions. First, let's talk about addition, which also includes subtraction. As you remember, subtraction can be considered as addition of opposite quantity. So we can add or subtract radicals. Sometimes we refer to these operations as combining radicals, as long as they have the same order and the same radicands. We can combine such radicals by combining their coefficients. The process goes nearly the same way as combining like terms in polynomial case. Let's see it. We need to add or subtract, or rather combine, these three radical expressions. At first, it looks like all radicals are different, so we can't really combine them at that stage. However, the first thing that we should do is simplify those radicals and then see if the result can be combined. Okay, so the first expression, 2 times root 12. We can rewrite root 12 as a product of perfect square number and something else. For example, 4 times 3. Okay, then minus 5, and let's split 48 into 16 times 3. And then plus 4. How do we split 75? Well, could be 25 times 3, right? 25 times 3. Okay, so we prepared our radicals to simplify. In the first expression, root 4 is 2, so we have the original 2 times root 4 is another 2, and times root 3. Then minus 5, root 16 is 4, so we multiply by 4, and times root 3. And finally, plus 4, root 25 is 5, times root 3. Okay, so now we multiply the coefficients, and we end up with 4 root 3 minus 20 root 3 and plus 20 root 3. As you see, in the end, we have exactly the same radicals, so we can just combine coefficients. 4 minus 20 plus 20 of what? Of root 3. Adding or subtracting radicals works exactly the same way as adding or subtracting terms in polynomial situation. So in our case, the 20 root 3 cancels the negative 20 root 3, and the whole expression ends up to be just 4 root 3 as a final answer. Okay, let's see the second example. This time the first two roots are cubic roots, and the last one is a square root. So obviously we won't be able to combine a square root with a cubic root, but maybe we could add these two cubic roots. Depends what they will turn out into after simplifying. So we have 9 cubic root of 16. Well, 16 can be split into a cubic number, 8, and 2. So cubic root of 8 is 2. We can write at once 2, and then we are left with cubic root of 2. Next, cubic root of 54. Can we split 54 into a perfect cube number and something else? Yes, that's 27 times 2. So cubic root of 27 is 3. We write plus 3, and cubic root of 2 is left over. Finally, we have minus square root of 8. So since this root is a square root, we are looking for perfect square number, which is 4 and 2. Square root of 4 is 2, and root 2 stays. Okay, in the end, what we can do is combining these two like terms. Only these two are like because we deal with radicals of the same degree with the same radicands. So here we have 18 of those, and then we add 3 of those. 18 plus 3 is 21 of cubic root of 2, and then minus 2 root 2. We can't combine these two radical expressions any farther because of different indexes. So that's the overall answer. In the next example, the first root is already in a simplified form, so we can just copy it. And in the second one, we have square root of 27. 27 can be split into a perfect square number 9 and 3. So square root of 9 is 3. The other 3 will be written under the root. But we also need to deal with square root of a to the 5. So let's recall that translates into division on exponential level, right? 5 divided by 2 is 2, So 2a's goes out and 1a stays under the root. Here it is. But now we see that these two terms have exactly the same roots. So yes, we can combine them by adding coefficients. But what is the coefficient in front of root of 3a? Well, it's 1. So we need to take 1 and then add this coefficient, which is 6a squared. At that moment, it's very important that you remember to place a bracket around the sum, because the whole sum will be multiplied by the root of 3a. Okay, so that's our final answer. And the last example, those roots are a little bit bigger. Can we simplify them? Since we have addition here, we need to factor the radicand first. So let's see it in a factored form. We can pull 4 out and then it's x plus 1. In the second root, again, let's factor the x squared out. So it looks like this, right? X plus 1 in the bracket. And then we are ready to pull something out of the radical. So in the case of first radical, we pull the 2 out, and then we have root of x plus 1 inside. And from the second radical, we can pull the x out, and root of x plus 1 here. For the sake of this exercise, we are going to assume that x is non-negative, right? Because we don't want to worry about absolute value here. But generally, if x would be any real number, we would be obligated to place absolute value. Keep that in mind. Okay, can we combine these two terms? Yes, we can, because the radicals are exactly the same. Therefore, we just need to combine the coefficients, even though the coefficients involve some variables. However, since we can't really perform subtraction on these coefficients, we need to place them in a bracket. So 2 minus x in a bracket and then times root of x plus 1. That's our final answer. You can also see this operation as taking the root as a common factor out of the bracket. And here we have a couple more examples involving some fractional expressions as well. So how can we deal with this? Remember, we can split the root over numerator and denominator. And this 2 in front really belongs to the numerator. So we can rewrite this expression as 2 root 40. But instead of 40, we can write 4 times 10 in preparation for future simplification, right? Over. And then we have root 9. Root 9 is doable, it's just 3. Minus 7 travels to the numerator, so it's 7 root 3. And in the denominator, we have root of 27, which factors into 9 times 3. That's useful factorization because root of 9 is 3. So we can simplify it to 3 root 3. And then we can reduce the root 3 from the top and the bottom, right? Which makes the two fractions having exactly the same denominator. So we can rewrite them with a single denominator 3 and then just place the numerator. In the meantime, let's pull the 2 out of this radical. So we have 2 times 2 root 10 minus 7. Overall, 4 root 10 minus 7 over 3. Here we go. Next example, this time we deal with cubic root. And again, split the cubic root into numerator and denominator, so we end up with cubic root of 5 over cubic root of a to the 6. Here we can simplify a bit because it's like division on exponential level. So it's 6 divided by 3 is 2. A squared goes out of the root, right? Plus 3a goes into numerator, and if we split cubic root to the numerator and denominator, we have in the top cubic root of 125. But 125 is third power of 5, right? It's a cubic number. So cubic root of 125 is just 5 over, and now cubic root of a to the 9. Again, division on exponential level is 9 divided by 3. It's 3, so a cubed is in the bottom. And now we can check if there is anything to simplify. Yes, it is. We can reduce 1a, that becomes a squared in the bottom, which makes it easier to write this whole expression with a common denominator, a squared. Okay, so the first fraction contributes root 3 of 5, and then we have plus 3 times 5 is 15. That's our final answer. Let's practice. Find the perimeter of the given triangle. Can you try it on your own first? And then come back to the video and compare your answers. We need to find perimeter, right? So we need to add all three sides, which is 3 root 20 plus 2 root 45 and plus root 75. Okay, let's simplify each root first. So we have 3, and then 20 splits into 4 times 5. So root 4 gives us 2, and root 5 stays. Plus 2 times, let's split 45 into perfect square number and something else. 45 is 9 times 5. So root of 9 gives us 3, and then root 5. And finally plus root 75. That splits into 25 times 3. So root 25 contributes to 5, and root 3 stays. Can we combine any of those expressions? Yes, we can. The two expressions with root 5 can be added. So we have 6 of root 5 and another 6 of root 5. 6 plus 6 is 12 root 5. And then this expression has to be just copied, plus 5 root 3. This is the exact value that represents perimeter of this triangle in inches. Now let's see how do we multiply radicals. We multiply radicals the same way as polynomials. We use foiling process and special formulas if possible. After any multiplication, we simplify radicals in each product. Obviously, if we talk about multiplication, we have in mind division as well, because as we remember, any division can be converted into multiplication by the reciprocal of the divisor. So let's practice. To multiply 2 root 5 times this bracket, we deliver this first term to each term inside the bracket. So let's multiply 2 root 5 times 3 root 5. Keep in mind this order. First check the sign. Well, in this case it's plus, so we don't have to worry. Then multiply coefficients, so 2 times 3 is 6, and finally multiply roots. Anytime we multiply root by itself, the root really disappears. So root 5 times root 5 is just 5, so times 5. And then let's go to the next term. Again, sign, negative. Numbers, 2 times 5 is 10. Radicals, root 5 times root 2, we multiply radicands, so it's root 10. Here we go. And this is nearly the end. We can't combine these two terms because they are unlike. However, we can multiply 6 times 5, so we can say 30 minus 10 root 10. Let's see the next example. What can we do here? FOIL. So multiply first terms, outside terms, inner terms, and last terms. Okay, first is first. Root 3 times root 6 is root, and we can say 3 times 6. But instead of writing 18, we can rewrite this 3 times 6 as 3 times 2 in preparation for simplification in the next step. Okay, now this times this. Sign, plus and minus gives us minus. Root 3 times root 3 is just 3. Now inner terms 2 times root 6, so as it is, plus 2 root 6. And the last term's sign is negative. 2 times root 3 stays as it is. Okay, the only thing that we can do here is to pull the 3 out of the first radical. So we have 3 root 2, then minus 3 plus 2 root 6, and minus 2 root 3. Are there any radicals that are like? No, so that's our final answer. There's nothing else we can do here. Next example. Oh, that could be a bit tricky because we have this cubic root. However, can we apply a special formula that will help us to multiply? Do you see these two brackets are really conjugates? So yes, we can. We can apply difference of squares, right? Square of the first term minus square of the last term. So square of the first term is just x, because if we square the root, what's left is x. Minus, and square of the last term, that's like cubic root of 2 but it is squared, so it's cubic root of 4. Unfortunately, cubic root of 4 can't be simplified, so that's our final answer, x minus cubic root of 4. Next, let's check those terms. They are exactly the same and opposite signs inside. That means we deal with product of two conjugates, which results in difference of squares, isn't it? So we square the first term. Let's write it down, 2 root 3, and we are going to square it in the next step, minus square of the last term, 5 root 2, and square it. Okay, now we can perform those squares. 2 square is 4, root 3 square is 3, minus 5 square is 25, and root 2 square is 2. Altogether we have 12 minus 50, which means negative 38. Nice answer. Finally, we have a perfect square of two terms. So this time we should apply perfect square formula. Just in case if someone doesn't remember, let me remind you the perfect square formula a plus b. When we square it, we end up with a square plus double the product 2ab and plus last term square b square. Okay, keeping this in mind, let's square this binomial. First term square is 9 plus double the product, so it's like 2 times 3 times root 5, so it's 6 root 5, and plus root 5 square, which is just 5. See, this formula makes it really easy. 9 plus 5 gives us 14, and then plus 6 root 5, and it's done. Here we go. Couple more examples. Again, perfect square formula. However, we have a minus inside the bracket, so the middle term will be negative. Okay, let's perform it. The first term, 2 root p, and we square it. Let's leave the squaring process for the next step. Then minus, double the product. So the product is 2 times 3 is 6, double it, it's 12. And then we have root p times root q, so root pq. Okay, last term plus 3 root q square. Okay, let's perform those squares. So we have 4 and square of root p is just p, 4p, minus 12 root pq, and plus 9 and just q. Okay, the following example looks really big, but again, can we apply special formulas to help ourselves? Well, yes. This first term, the whole bracket, is exactly the same, and the last term is exactly the same. Since the brackets have different signs, we apply difference of squares, treating the first inner bracket as our big first term. So we're taking root 5 minus root 3, the whole thing as a first term, and square it, minus the last term, root 6, and square it. However, now when we need to perform the perfect square of this difference, we use perfect square formula. So that's our first term, that's our second term. We're squaring the first term, which gives us 5, using the middle sign, taking double the product, so it's 2 times root 5 times root 3, so it's 2 root 15, and squaring the last term. The last term is always positive, right? So plus 3. Now, copy this minus, square the root of 6, which is just 6. Okay, and finally, we need to combine like terms. So this 5 plus this 3 is 8 minus 6 gives us 2. And copy the negative 2 root 15. That's the final answer. The last example, perfect square of a binomial again, but those terms are a little bit bigger here. So let's apply the square of the first term. So it's root of x plus 1 and square it. Then minus, double the product, so 2 times the first term times the second term. And plus square of the last term, so it's root x minus 1 and square it. That gives us just x plus 1 from the first term, because the root will be cancelled with the square, minus 2. And now we can multiply these two radicands. However, again, observe that x plus 1 and x minus 1 are conjugate brackets, so when we multiply, we end up with x squared minus 1 as a difference of squares, right? And then plus this root disappears because of the square. Okay, overall we can combine like terms, so x plus x is 2x, the plus 1 cancels the minus 1, and then we have negative 2 root of x squared minus 1. That's our final answer. There is nothing else we can do about this. The terms are different, and also we can't pull x out of this radical because of this minus. The x squared is not a factor, so don't even try to pull x out of it. That's all what we can do here. Now it's your turn. Practice a lot.